So here now we'll study about di by dt and dv by dt limitations. What is the di by dt and what is a dv by dt concept, and how it is useful, and how why it is it has to be taken into consideration, and what is the snubbers and how to design the circuits, design methods and design considerations for designing these number circuits, and all those things we'll be seeing in this particular concept of a lecture. So see here now. Di by dt and dv by dt. We are talking about di by dt. It means we are talking about the changing of current with respect to time. What will happen? What are the limitations if a current changes with respect to time? And also, what are the limitations of voltage supply, or the voltage differences or potential differences changes with respect to time? What are its limitations? So let us see those things now. Transistors require certain turn on and turn off times. We know that the transistor switches from 0 to 1 and 1 to 0. There will be a continuous switching between a transistor from 0 to 1 and 1 to 0, 0 to 1 and 1 to 0. It's a switching time. Switching time will be there. So now from that on we can understand that whenever a transistor is switching, depending upon its voltages which we apply, if let me say, if I have given a gate voltage of 0 to the P transistor, or let me talk about the MOSFET. If I give a voltage of 0 volts for a gate of PMOS, what will happen? The PMOS is going to turn on. This is the PMOS symbol, how it looks like. So here, if I trigger it with the 0 volts, this PMOS is going to turn it on. And similarly, if I trigger this NMOS, this is a NMOS symbol. If I trigger it with 1 volt, high volt, in fact, we can call it as a low voltage and high volt, low state of voltage supply and high state of voltage supply. If I give 1 volt for this NMOS, NMOS will turn on. So what's actually happening? Depending upon the voltages levels, the particular transistor is turning on. It means it is switching from on state to off state and off state to on state. That's what is given here. The transistor requires some certain turn on and turn off time. It will be in the period of on state for some amount of time. It will be in the state of off state for some amount of time. That is what we call as a turn on and turn off time. Now, the typical voltages and current waveforms of the BJT. Here we'll be talking about in with respect to BJT itself. So that's why the typical voltage and the current waveforms of BJTs has given below. Now here, if you see the structure of the waveform of this one, during the turn on, what happens in the BJT? Whenever the BJT is turned on, the current of the collector rises and the di by dt is given as. We know that whenever the BJT is turned on, there's a complete working procedure of a BJT. Well, what will happen? Definitely on the triggering of that particular emitter will definitely, what is the charge moves from emitter to base and from base to collector. So whenever the charge is moving from emitter to base and base to collector, ultimately the charge gets settled in the collector. So the settling of the charge in the collector, it means that the current is stored at the collector terminal. So that's what it's given here. Whenever during the turn on nature of the BJT, the collector current rises and the di by dt is given as di by dt. Let us see this formula now here. Di by dt. It is a change in current with respect to time. Why we call it a change in current with respect to time? Why? Because it will not be the same amount of charges moving all the time constantly from emitter to base and base to collector. The number of charges which are moving from emitter to base and base to collector will be changing with respect to time. So that's why we have written it as change in current with respect to time, that is di by dt. That is given as what? IL by TR. IL here we will be talking about the load current, and then TR is a rise time. Okay, we are talking about the transition time, or the time of this particular uh, uh, what is that device operation or the current moment. See here, actually it's actually transition time. Why I should not directly call it a rise time? Why? Because here, if you see the waveform, in the waveform here, the current here it's rising over here. Again, it is the waveform it's falling here. This time is a transition time. Actually, I should call it is transiting from zero level to high level here. And again, coming to this part, it is transiting from high level to zero level. So it's a transition time I should call. In fact, if I go very particularly, it should be rising time from zero to high. And again, in the same way, from high to low, it should be the fall time. It has to be fall time in particular if I need to talk. Or else, as of now, it should be taken as a transition time. IL by TR, that is equal to ICS. What is that IL? It's at the load. So that's what it's at the collector current divided by it's a transition time. It's an amount of charges moving with respect to some amount of time. So that's why it's a current by time. Now, during the turn of nature, this is an operation which happens in the turn on nature. Now, during the turn of nature, the collector and emitter voltage must rise in relation to the fall of the collector current. During the turn of nature, what happens during the turn of nature? Definitely, it is your BJT will be in the off state. I mean, your BJT will enter into the reverse bias operation. Whenever it's reverse bias, the BJT will not be working. There will be no operation of the charges because of the depletion region. The depletion region of the BJT will increase. That will not allow the charges to move across this. What is that? Across the junction. So because of that one, during the turn-off region, the collector emitter voltage becomes the most important parameter. The collector voltage must rise in the relation to the fall of the collector current and the dV by dt, the change in voltage. Why does a current? Why when a CNO? We have studied one Ohm's law where it is a that current which is passing across this particular junction. It is directly proportional to the voltage. It is directly proportional to the voltage which you have already studied over here. So now, as for the Ohm's law, if the current is changing, definitely the potential difference across the conductor also changes. So if current is changing means voltage is also changing with respect to time. The current doesn't all of a sudden it is not going to fall. It is going to change. It is going to decrease slowly with respect to time. That means the voltage potential is also going to decrease with respect to time or change with respect to time. So that's why the must rise in relation to the fall of the this one. What is that? Current. So dV by dt is given as dV by dt is equal to source voltage at the source divided by TF, that is equal to VCS by TF. So these are the two important equations which are regarding the turn on and turn off nature of the particular transistor. Now let's see. During this time, we are supposed to maintain the device. Why? Because all of a sudden, if the current is rising or all of a sudden the current is falling, that might degrade the operation of a BJT. So that's why we are going to study about this concept called as di by dt or dv by dt limitations. There are some limitations which are supposed to be kept in mind. How to tackle with or how to deal this rising of current rapidly or falling of current rapidly. Or we can say that it's all about the performance of the particular device. That's very important concept. Now, protection circuits are normally required to keep the operating di by dt. We are talking about the protection circuits. We are supposed to be very much aware about the device, and we should need to protect the device. That is with respect to the operating di by dt and also dv by dt within the available limits of a transistor. Every transistor up to now we have seen di by dt and dv by dt. But in the previous lectures, we have seen about the design parameters where we have studied even about the what is the ratings of the transistor, current ratings and voltage ratings. That ratings of the transistor with respect to the allowable every device it has got its own allowable limits of the current and voltages. So you're supposed to make sure that the protection circuits are used in order to protect the device and to make sure that di by dt and dv by dt is within the limits of the allowable concepts of the transistor. Now, coming to the typical transistor switch, let us see how it works. We are talking about the typical conventional transistor switch with di by dt and dv by dt protection is shown here. So, see now. This is a circuit where you can see a transistor here, the BJT, BJT is given over here. This device where you can see one diode is connected. Then again, LS, there's a inductor connected. Inductor is connected here, and the load current. The load current is flowing through the resistor, and again another inductor. And at the output part, we are having this capacitor, which is connected to the resistor, and also one diode at this capacitor. It means this is in between. This output circuit is in between the collector terminal and also the emitter terminal. At the base terminal, you see one resistor, which is a base resistor, and this is your biasing voltage, which is connected between this base and the emitter. And ultimately, between this terminal and this emitter terminal, there is a source voltage Vs. So this is your protection circuit, which is one of the protection circuit for this uh, to limit keep the limit of di by dt and dv by dt. Here now. First of all, this is a base voltage, bias voltage. Actually, it's not base voltage; it's a bias voltage. Bias voltage. Initially, the bias voltage is kept at the high level up to over here, and then the bias voltage has been dropped to zero and to this particular part at the T. Then, as per that one bias voltage, then the flow of current. Flow of current is most important. Why the flow of current is most important? Because we are talking about a BJT. BJT is a current controlled device. It's not a voltage controlled device. It's a current controlled device. When you're talking about the BJT, you'll be talking about your operation and its waveforms in the current controlled operative manner only. So that's why initially the current will not be rising directly to the high state. Slowly, with the increase of the what is that movement of the charges, the current rises, and at some particular level, it comes to the maximum level. Maximum level. So this is a rise time, and also this is now here. Depending upon the switching nature, it is going to fall down. Okay, this is a TF. This is a fall nature, right from here to here, and this is we call as a rise time or the setup time from here to here, and this is a whole time where the current has been stable over here. Next, there's other operation. In this way also we can see in the reverse manner. So this is how your protections are. This is the waveforms regarding this protection circuit where you are trying to hold this current motion at some particular time without degrading the operation of your circuit. Without degrading the operation of your circuit. Now, if you see the circuit operation, let us see that how it is working here. RC, we have used the RC here. We will talk about this RC and all those things. An RC circuit is used. RC circuit is used. What is meant by RC circuit? We are talking about a resistor and a capacitor circuit. So we have used here an RC circuit. We have used this RC circuit or not? We have used here one RC circuit, and this RC circuit only they are talking here. The RC circuit is used across the transistor is called as a snubber circuit. Snubber circuit. What is a snubber circuit means? The RCs, whenever you connect this RC circuit in this manner, we call it as a snubber circuit. Why we use this one? We use this snubber circuit in order to limit the dV by dt concept. Okay, dV by dt parameter. In order to limit this dV by dt, we use a RC circuit which is called as a snubber circuit. Now then the LS is used. The inductor LS is used between the collector and the voltage source. This is a LS inductor. This inductor LS is used between the collector and voltage source, which limits the dV by dt. The operation of this LS is what? It is used for limiting of the dV by dt, and it is called as a series snubber. It is called as a series snubber. So we have talked about the snubber circuit. There's RC circuit, which is used for limiting of the dV by dt, and the the inductor LS is used for limiting of the di by dt, which is called as a series snubber. Now, under the steady conditions, now here, whatever the whatever the waveform I have explained there, we'll try to see that waveform in detail right now here. Under the steady conditions, the load current, there is IL, is freewheeling through the diode DM. We are having a diode at which is connected over here. The diode is connected here. This DM. So now your IL, there's a load current will be freewheeling. It will be freely moving through the diode DM, which has a negligible reverse recovery time. We know we have studied about this reverse recovery time and all those concepts in the diodes, PN junction diode. Now let us move into that operation. When the transistor Q1 is turned on, when a transistor Q1 is turned on, transistor only one transistor we are having BJT. Whenever it is turned on, when that particular transistor is turned on, IC rises. IC is what? It is the current at the collector. Whenever a transistor Q1 is turned on, the current at the collector rises and the current of the DM falls. The current of the DM falls. Why does the current of the DM falls? Because the DM behaves as a short-circuited nature. If you see the circuit diagram over here, see now. This is how it is connected here. Where is this connected? If the current is rising, whenever the transistor is turning on, whenever the transistor is turning on, if more amount of current is flowing in this direction, here the collector part, the DM it will act as a short circuit nature. It is going to act as a short circuit. The current will be falling here. This particular DM will be acting as a short circuit. What is DM actually? It's a diode. See, we have studied about that. What is we have studied about the operation of a diode. The diode will be working only in one direction. That is, this is a forward nature of the diode. It works from anode to cathode only. The current flows from, or the charge flows from anode to cathode. But here, when you talk about this collector is connected to this one, and the direction of the current you can see over here, it is in the reverse direction. So the current over in this one DM is not going to work properly. So that's why we have written here, whenever the Q1, there is a transistor is turned on, I see there's a current at the collector is going to rise and the current of the DM falls because DM behaves as a short circuited. The DM is going to behave as completely as a short circuit. Because of that one, the current is going to fall in the DM nature. In the DM, that's a diode. The equivalent circuit during the turn on nature is given over here. There's an equivalent circuit of that one. We have seen just now. This one is going to act as a short circuit. This is a short circuit diagram which is mentioned over here. It is acting as a short circuit nature. Because of that, the current will be falling in the diode and the current will be flowing in this one. This particular part will act as now the current source. This particular branch where you have seen in that main circuit diagram, there is one resistor is present and also one inductor is present. So this branch will completely act as the current sourcing branch. So that's why instead of that, giving those two parameters, they have mentioned there one current source here. Now let us see that one. Di by dt. Di by dt is mentioned as per your, for this particular branch, we can write it as di by dt is equal to Vs. That's a voltage which is at this part divided by the current, what is that, the inductance, the current flowing through the inductance. So di by dt is equal to Vs by Ls. This is equation number 3. And now we have got the equation 1 also there, which earlier we have written over here. Di by dt is equal to, in the equation 1, that is ICS by TR or else IL by TR. So now let us see this one. Let us try to equate this one. When you equate, let us see how it works about. Now, when you equate those equation 1 and equation 2, you're going to get the value of the IS. So this is the design parameters how we are supposed to find out. Vs into TR divided by IL will give you the value of the LS. That's the value of the inductor. This is all about, see, we are trying to find out the LS in order to find out what is the value of that inductor. So this is a design parameter part, equation number 4. Now let's see the turn off nature. During the turn off nature, we know that the capacitor is present at the output. We have seen the capacitor at the output in the circuit. The capacitor during the turn on nature, the capacitor is going to charge up. Now during the turn off nature, we are talking about the turn off of a BJT. So now The capacitor CS charges by the load current, and the equivalent circuits looks like this. The load current, because of the load current, the capacitor will be charging. Now here, that value, the voltage across this capacitor is given as dV by dt is equal to IL by CS. Equation number 5. Now let us equate equation number 5 and equation number 2. Well, we get your equation as CS. This is the value of capacitor. CS is equal to IL into TF by VS. That's equation number 6. Once the capacitor is charged, once the capacitor is fully charged to the voltage Vs, what happens? The freewheeling of the diode turns on. When the capacitor is fully charged, then again the diode freewheeling will be turned on. Due to the energy stored in Ls, there is a damped resonance circuit. Now here we have talked about the resonance and the damping nature of the circuit. So see, that thing we are talking over here. Once the capacitor is fully charged, what will happen? The freewheeling of the diode. Here, especially actually here, you are having your BJT like this, okay, and this is connected to this voltage current source, and here from here you are having a what this is your uh, diode, and this diode is connected over here again. So now, whenever the capacitor is fully charged, the freewheeling of this diode takes place. Once the freewheeling of diode takes place, due to the energy stored in the LS, that's this one, the inductor LS, what will happen? There is a damping resonance circuit will be created. This will act as a resonance circuit. So you can see now. This is the equivalent circuit of that one. How it looks like. Just now we have drawn with the inductor, transistor, and all those things. This will act as a damping resonance circuit. The RLC. Now we are having your RLC, R, L, and C. The RLC, this is a capacitor, is a C, R is a resistor, and L is a inductor. The RLC circuit is normally made critically damped to avoid the oscillations. Why we are using this RLC circuit over here? We are using this parameters. We are finding out the values of L, C, and R. The main reason is that we do not want any kind of oscillations at the output. There should not be any kind of oscillations at the output. The output has to be very stable. So in order to avoid this kind of oscillations at the output, we are using the this RLC circuit. For critical damping, the conditions, these are the conditions when this symbol, when eta is equal to 1, which yields RS has to be, the value of RS has to be 2 times of square root of LS by CS. This is about your equivalent circuit of this one, of a particular dV by dt circuit design. In the next lecture, we'll be trying to study about the design consideration, how to design the snubber circuit and the uh, snubber circuit diagrams. We have talked about the snubber CS, right? We have talked about the snubber circuit, which is mainly used for to limit what is that di by dt, and the series snubber is used for di by dt, and also the snubber circuit is used for limiting of the dV by dt. So this was about snubber circuits and how to limit the di by dt, and which parameter is used for limiting the dV by dt, and which is used for limiting the di by dt. We have seen in this lecture, and in the next lecture we'll try to see about the design parameters, how to design those RLC. Why that RLC is most important? RLC is most important in order to avoid the oscillations at the output. So to avoid the oscillations at the output, we are trying to design that parameters for this circuit. So that thing we'll be seeing it in the next lecture. I hope it's clear to you, and this lecture is clear to you.